Morning, everyone. A very warm welcome to today's masterclass of SaiU Pathways, a masterclass series organized by Sai University. And today's masterclass is organized by the School of Computing and Data Science, which is titled From Cloud to Chip, Can AI Go Tiny? It is my pleasure to introduce our distinguished speaker for today, Dr. Ashok Chandrasekaran. Dr. Ashok Chandrasekaran brings nearly a decade of teaching and research experience in the field of signal processing, special focus on array signal processing for radar systems and emerging 6G wireless technologies. He has worked on prestigious research projects at institutes like Central Electronics Engineering Research Institute, CERI, where he contributed to the development of mission vision system, and at IIT Bhubaneswar, where he was involved in direction of viral estimation research. Dr. Chandrasekaran has published widely in reputed platforms such as IEEE, Springer, Elsevier, FAIR, and was also honored with the IEEE Publication Award in 2021 by the IEEE Madras section for his innovative work on machine learning inspired DOA estimation. So he also holds published Indian patent in the domain of passive radar applications. In addition to his research, Dr. Chandrasekaran actively contributes to the academic community as a peer reviewer for leading journals including IEEE Transactions on Vehicular Technology, IEEE Sensor Journal, and several Elsevier and Hindu publications. We are delighted to have him with us today. And welcome, sir. Over to you.
So, thank you, Mr. Nelly, for introducing me. So, good morning, everyone. So, before that, am I audible? Am I clear?
Yes, sir. You're visible, audible, and your screen is shared. Yes.
Okay. Right. Thank you. Thanks for confirming. So, yeah, formally, good morning, everyone. And so, topic of my talk for this session is from cloud to chip. Can A go tiny? Right. So, in this one hour talk, so we will explore the new world of AI. And that's what primarily we are going to focus on. So I will try to bring it uh, as close to you as possible. So I will reveal what exactly the new world of AI may mean shortly. So as we are going to talk about AI, so it is better to understand AI in a systematic way that will help us to understand or follow the talk better. Okay, so before that, a small note. So I have tailored this presentation in such a way that those who are completely new to AI can also follow. So we are going to talk about a lot of technical aspects, but everything from an elementary point of view, so that everyone can follow. So that's the fundamental idea of this presentation. Okay, so let us begin our discussion with what exactly AI is, and what is machine learning, and what is deep learning. So, as you see, AI refers to the simulation of human intelligence. So, it's basically the process of mimicking the intelligence or behavioral patterns of humans or any other living entity. So, if you look at the overall goal of AI is to enable the computers, to perform cognitive tasks in wide range of areas like how humans would. So that's the overall goal of AI. For example, how to understand this? For example, an AI system that can recognize faces in a photo, right? Like how humans recognize people, right? This is an example through which you can easily relate what exactly I mean AI. And coming to the machine learning is a subset of AI. As I said, so we need to enable the computers to perform task like faces in a photo. Achieve all this, so we need to train the computers to learn from data. So we need to train the machines. So machine learning is a computer can learn from data without, just a second, And what is deep learning? So deep learning is another subset of artificial intelligence, and that is actually inspired by human brain neural network. So deep learning is a technique within machine learning which uses artificial neural networks to learn complex patterns. So overall, if you look at, so the whole idea of artificial intelligence is to simulate the human intelligence to perform some cognitive task. And for that, we need to, train the computers to learn from the data. That is what machine learning is all about. And deep learning is within machine learning that is actually inspired by human brain neural networks, which uses artificial neural networks to learn complex patterns. This is what AI, ML, and DL is all about. Now, here is a snapshot to compare the biological neural network with artificial neural network. So, the biological neural network, if you look at, it's a very complex, network of neurons. Millions and millions of neurons are there here. And if you just see the artificial neural network, it consists of input layer and some hidden layers and output layers. So anyway, so we are not going to get into the details in this session, but I would like to give you a brief idea about what exactly AI is and what exactly embedded AI is. That's the world I'm going to talk about, and what are the challenges and how a simple math can help to resolve their challenges. So that's what primarily we are going to focus in this presentation. So yeah, coming to this. So here you can see the input layer is basically, receives the data, and output layer is going to provide the results like decision or predictions in simple terms. And what about this, hidden layers? Hidden layers, it's a complex network and lots of connections you can see here. And these connections are usually referred as adjustable synapse. And this is a place where exactly the computations are going to happen. Heavy computations are going to happen. And and we need to this, as I said, like this connections represents the adjustable synapse or nothing but weights from an artificial neural network point of view. All of these weights are trained during the learning process. Anyway, we need to adjust all this, weights and bias, and that's where all the computations, heavy computations, takes place. Okay, so here is a snapshot, and this is a snapshot which compares the biological neural network and artificial neural network. And so that I'm not going to get into the details, and that is what primarily we'll look at in a typical machine learning course at undergraduate level or at higher education level. So this session is not intended for that. This session is to gently introduce the concepts of embedded AI and what are the challenges and how the challenges can be resolved by using some simple mathematical concepts. That's what primarily I'm going to focus on. Okay. So now I would say you can find A in almost every area, right? So you can see everywhere, you know, AI-based applications starting from which includes analyzing the images and processing text and speech and making some recommendations, right? So most of these applications are powered by machine learning. So behind the scenes, if you look at any AI-based applications, it's all powered by machine learning. So that's the reason why I started my presentation with what exactly machine learning is. Okay. So now let us go further into it. What are the applications? So there are different classes of problems you can solve using machine learning. So machine learning, again, I repeat, machine learning is basically allow the computers or the digital machines to learn from data. That's what machine learning is all about, without using any complex tools. So as we proceed later during my presentations, I will introduce a simple mathematical uh, uh, task through which easily we can understand what exactly the machine learning is. So just stay with me. I will reveal in a while. So coming back to this applications. So as I said, image classifications, object detections, and segmentations. Everywhere we use machine learning. So what exactly image classification is? Let us understand from an AI perspective. So image classification basically tells us what is present in an image. For example, if a model, here you can see um, an image is shown to a model, then model decides whether the image is cat or dog in this case. This is what I mean image classification. And object detection is basically to detect multiple objects in an image. So here you can see. So here there is a picture and here cat, duck and dog. So the whole idea of this application is to detect all the objects present in an image. This is a hairline difference between classification and object detection. And image segmentation, this goes one step further. So it's basically to classify the pixels and to give a precise informations about the objects in a scene or in an image. So this is widely used in autonomous driving vehicles, basically to identify trucks, roads, uh, cars, and pedestrians. So all this application, these are all image based applications, and now all these image based applications are powered by AI, specifically machine learning. So just a check. So Mr. Nellai, everything goes fine. So am I clear and audible? Uh, Anyone of you kindly respond? So am I audible and clear? Okay, right. So this is all about image-based applications. Now coming to the language translations. Here is a snapshot. So what exactly language translation is? So it's basically to convert a text from one language to another language. So how to understand this? It's simple. That's nothing but your Google Translate, which helps you to convert a text from one language to another language. Latest, current language translation models are powered by machine learning. And recommendation systems. So as we know, basically it suggests recommendations based on user behavior, which you can find it in Netflix movie recommendations or YouTube videos and Amazon products. So all these applications are powered by machine learning. Now, let us look at an important question, that is, can machine learning make mistakes? A very interesting question to look at. Yes, machine learning models may result in wrong outputs. The reason is machine learning is a stochastic model. So what I mean stochastic model, machine learning models work on probability, not certainty, which means it learns pattern from the data and it makes prediction or decision based on what it has seen before. That's why machine learning models make mistakes, may result in wrong outputs. For example, here you look at there is a cat picture given to the machine learning model, and machine learning model looks at this picture and predicts that it has dog because of its stochastic nature. Stochastic in the sense probabilistic nature. So machine learning models do not think like humans. Please understand. So we are trying to make the computers to think and behave like humans. How it's possible? You need to train the machine learning model with humongous amount of information so that the machine learning models can learn the complex patterns from a data. So this is a critical point that you need to understand. Yes, machine learning models can make mistakes, but you can strive to make the machine learning model more accurate through the process of training and by tweaking other aspects of machine learning, right? So now coming to the infrastructures. So all these applications, all these applications, if you look at, when we use machine learning, definitely it requires high computational power, no doubt about it. So because machine learning is power hungry, so that's why we need to use TPUs or GPUs. TPUs are nothing but tensor processing unit and graphical processing units. If you look at from an infrastructure perspective, so to run a machine learning model or to train a machine learning model, we need a big computing facility. Not just one, please understand, not just one TPUs or GPUs. You need to stack them together in a large data centers. So that's what I mean the cloud. So we always try to train the machine learning model using cloud. The whole idea of this talk is to move the machine learning model from cloud to chip. How? Let's figure it out in a while. So again, I repeat, machine learning is power hungry. So that's why we need GPUs and TPUs, high computing systems, not just one. Again, I repeat, you need to stack them together. Here you can see stack them together in a large sized data centers. And usually these data centers are located near sea. So for the purpose of cooling. And I would like to add one point with respect to the responsible AI here. So why usually the data centers are located near sea? The idea is very simple. So it's going to perform heavy computations and it is going to release some significant amount of carbon footprint. So that's the message, right? So just like that, you should not hit the cloud to train a machine learning model or to make some inference with the machine learning models. Try to move from cloud to microchip or to some local devices. That's the fundamental idea of this talk anyway. So you will get it shortly. Now, this is what about AI and some of the potential applications of AI that are covered by machine learning and about the computing infrastructure. Now, let me take you all into the new world of AI. So, let us understand this through some potential forward looking applications. So, for example, when you say, OK, Google, to a Google Nest device, Google Nest is a small. Oh, my machine wakes up actually when I say, OK, Google, because all smartphones, my phone is an Android phone, it wakes up. So you can also try that. So when you say, OK, Google, your system or otherwise your smartphone instantly wakes up and start responding to it, right? Yeah, you can also see it in Google Nest. Okay. Oh, it's responding. And so this is one applications, Google Nest applications is a small embedded device. And autonomous drones are basically, you know, a group of drones that operates completely independent for different applications which you can think of. And there is another application that is smallest pacemaker. This is Medtronic's Micra AV is the world's smallest pacemakers. So that can directly go into that can be directly implanted inside a heart. So this is a world's smallest pacemaker. This is an electronic device, very small electronic device. Just imagine if you enable this electronic device with machine learning smarts or machine learning capabilities or AI capabilities, then you can do a lot of things, right? So you can assess the heart's health periodically and you can do lots of valuable analytics. And coming to this Google Lens, or Google Glass, or otherwise Smart Glass in general, let me give you an example to understand this. For example, if you are in a new country and someone is talking to you in a language that you are not comfortable with, just imagine your smart glass converts the language into the language that you are comfortable with in real time. So that's cool, right? So these are all some of the embedded devices or small tiny devices available. And now the question is, if you enable all these devices with machine learning smarts or machine learning capabilities, and you can do lots of things. So that's what embedded AI is all about. I'll come to it. Just stay with me. And coming to the neural link, Elon Musk project. So it's basically what? It's basically a small chip that helps to understand the brain's activity. So why we want to understand the brain's activity, how brain actually works. So you can do lots of things, right? So we can, provide treatment to some of the critical conditions like depressions and neurological disorders. All that we can do. And here, this Alexa is similar to the Google Nest. Alexa, Hey Siri, these are all keyword spotting applications. A small embedded device which wakes up when you say some word like, okay, Google, hey, Alexa, hey, Siri, right? Again, my machine wakes up because I said, okay, Google. So these are some of the forward looking applications currently we have. Now the question is, if we enable the machine learning smarts or machine learning intelligence in all these devices, then you can do lots of things. But the question is how to enable it. Because just I said, machine learning models are power hungry. It requires heavy computation power. That's the reason why you need data centers, right? And you need millions and millions of TPUs and GPUs, to perform that heavy computations. Then how it is possible inside a small device like Medtronic, Micro, or Drone, or Google Nest, or smart glasses? Anyway, so that's the. Just stay with me. I will reveal it. So coming to the social applications of embedded AI. So this is an interesting initiative by uh, so many organizations because there is a pressing situation in Africa for diminishing elephants populations. So that's why the organizations like Egypt's Microsoft, here you can see so many organizations coming together to develop an AI-based solution to monitor elephants' movement and to protect this gentle beast in Africa. So this is so machine learning is not only for commercial uh, applications. There is a social application of embedded AI. So here is the snapshot. Elephant Edge is a project, and so many big companies are involved in developing AI-powered solutions to protect elephants diminishing populations, basically to monitor elephants' movement in the forest. So especially in the Africa. So you can explore about what exactly that system is and how small that system is. It's an elephant collar, right? It's a small embedded device that helps to monitor the elephant's movement and sounds and all that. So once the data is available, then we can do lots of things with that data. Okay. Now, yes, the other applications are IoT 2.0, that is intelligence of things. So AI plus IoTs. Now we are surrounded with lots of IoT devices. IoT devices in the sense there are lots of smart devices around us. And just imagine if you enable AI in IoT, you can do lots of things. So that is a statement. And much of it from IoTs. As we know that data is a fuel for AI, right? So we need data. We need humongous amount of data to train the machine learning models, right? So that we can mimic the human intelligence. But if you look at from an IoT point of view, there are close to approximately 5 quintillion bytes of data are generated every day, and much of it from IoT and digital systems. We are utilizing 1% of that. What if we utilize that 5 quintillion bytes of data? We can do lots of things. There are n number of applications which you can think of around AIoT, that is artificial intelligence come Internet of Things. That's what Internet of Things 2.0. So these are all some of the applications just to set the stage, um, to understand what exactly the embedded AI is. So anyway, I will talk about what exactly embedded system I mean. So just stay with me and let us look at the potential of embedded AI through the lens of market size. So here you can see there is an exponentially increasing trend. So it is forecasted that 21.9 billion USD, which is approximately 2 lakh crore in Indian rupees. So that's what the market forecast in 2030. By 2030, so the embedded AI market reaches to 29.1 US billion USD, which means 21 lakh crore. That's the market size. There is a big space for embedded AI from a marketing perspective. Now, the whole idea of embedded AI is basically to move from cloud to small, tiny, ultra low power device. That's what the fundamental objective of embedded AI. It's not just moving from cloud to smartphone. Smartphone is just an edge device. So I'm talking about something called tiny devices in the sense ultra low power devices in terms of limited computation power, memory, and size. So example, smart glasses, small sized, pacemakers, small embedded devices can be referred as tiny devices. So how to enable the machine learning smarts or intelligence in all tiny embedded devices? That is what we are interested in. So you can move from cloud to edge. That's not a big deal because most of the smartphones comes with a significant compute power and memory space, right? So 8 GB RAM at minimum or 4 GB RAM at minimum. So you can do lots of things. But the question here is the embedded systems are usually, you know, comes with extremely low compute power and memory size. That's the reason why enabling machine learning smarts or machine learning intelligence in a small, tiny devices is a challenging task, right? So that's what I mean, the new world that is embedded AI. So moving from cloud to small microcontroller or small chip. Okay. So if you have any questions, just make a note of it, and so you can also ask in between. Just raise your hand you know, and you can ask in between, or else you just make a note of it, and then end I can answer some of your questions. So just a second. Right. So coming to the embedded systems, so I talked about embedded AI. Now let us go one step further and understand what exactly the embedded systems I mean. So if you look at here, embedded systems is basically a small, tiny computing device that comes with limited computational power, memory, and limited software portability. So I'll come to software portability. Just stay with me. So here is a snapshot, and here you can see, sorry, here you can see the form factor of big CPU and GPU and the form factor of small microcontroller uh, units, MCUs, microcontroller units. So again, I repeat, embedded system is a small, tiny computing device limited with less compute power, limited with less memory space, and limited with software portabilities. That's what embedded system is all about. So here you can see the form factor of a big GPUs, that is 561 millimeter square. That's a die area. And if you look at the microcontroller, the world's smallest ARM-powered microcontroller unit, so it's of dimension 3.2 millimeter square. It's extremely small. And in a stock laptop, you have the flexibility in general computing machines, for example, Apple laptop or otherwise HP or any brand laptop if you take. So if the stock RAM is of 8 GB, then you can scale it up to 16 GB or 32 GB. But whereas in microcontroller, it comes with a package and you don't have any privilege to scale the RAM or to increase the compute power or clock speed. So that's what embedded system is all about. Because embedded systems are intended to perform a specific task, whereas general computing machines to perform beyond that. So that's what you need to understand. So here is a comparison. So here you see this is actually a small microcontroller, and you just look at this is positioned here with reference to the golf ball. We know how small the golf ball is, and if you look at the size of this microchip, it's extremely small. If it is extremely small, and think about how we can enable the machine learning smarts into it is something we need to think. It's possible here in big data centers, you can do it because that comes with heavy compute power and large memory space, and there is no issue of software portability and all that. But when it comes to this microcontroller units, it's a challenge. And now comparing the yeah. So now let us compare the compute power. So I mentioned about the compute power. Now let me talk about what exactly the compute power is. Big GPUs and CPUs, central processing unit, graphical processing units, or tensor processing unit, usually consumes hundreds of watt power to perform any computations. So it consumes more power in terms of hundreds of watts. Whereas if you look at a small microcontroller units, that is MCUs, it's all ultra low power, which means it consumes microwatt powers, 10 power minus 6 watt power. And if you look at the RAM size is 128 KB. Just think about it. It's just hundreds of KB, and the size is 2.52 millimeter square. So this is what we have, and now we need to enable the machine learning smarts into it, right? So embedded systems, microcontroller units especially consumes power in terms of microwatts, whereas the big CPUs or GPU consumes 300 watts of power. And as we know that this is 140 microwatt means you can operate this device by using a coin cell battery. Whereas GPUs and TPUs, you need a dedicated power source. So whereas all microcontroller devices can be operated with a coin cell battery. Here is a snapshot. Now coming to the challenges, let me explain a bit about what exactly the challenges are in embedded system. So embedded hardware is extremely limited, as I said, in terms of performance, power consumption, and storage. And embedded software is not as portable and flexible as mainstream computing. So, for example, most of the mainstream computing machines, GPU, CPU enabled computing machines, run with operating systems. For example, Raspberry Pi to some extent. Raspberry Pi is a single board computer. It's not a microcontroller. Please make a note of it. So the Raspberry Pi, I think most of you might have experienced Raspberry Pi for some experiments in your school time. So it's a single board computer. It's not a microcontroller unit. Whereas Arduino, it's actually a microcontroller unit that runs without operating systems. Without operating systems, in the sense, so everything has to be written in bare metal programming, which means it accepts or it supports C++ bare metal programming or Arduino Sketch. Whereas this Raspberry Pi actually supports Python. Um, and moreover, Arduino boards. Arduinos are microcontroller enabled embedded devices. So as I said, it typically run without operating systems. Typically, in most of the uh, Arduino based MCUs. But if you want to enable machine learning, as we know that machine learning completely rely on floating point operations. Floating point operation in the sense precise numerical values. But all these devices lacks, especially the Arduino MCUs, lacks floating point hardware unit. Then how to enable? So you can run machine learning model inside Raspberry Pi, but running a machine learning model inside Arduino board is extremely difficult. Why? Because again, I repeat, machine learning model rely on floating point operations, and most of the Arduino based MCUs, microcontroller units, lacks hard floating point hardware unit. So that's a challenge. It handles all the numerical values in terms of integer 8. Integer 8 in the sense integers. In simple terms, just whole numbers. Whereas floating point, I mean decimal numbers. Because the precision is required when it comes to machine learning computations, whereas for embedded task, so we don't want that level of precisions. That's the reason why Arduino boards comes with intake unit, in the sense integer unit, and it lacks the floating point hardware unit. But your Arduino do not natively support Python. So that is again a challenge. Most of the machine learning codes are in Python. So you cannot just like that flash any machine learning code inside Arduino board. So I'm getting a message like internet connection is unstable just to check uh, is everything fine and are able to follow. Just
Yes, sir, you're audible. Yes.
sure. Okay, thank you. Right. So this is what I mean, the limitation in terms of embedded software portability. So there are lots of challenges and constraints. So when it comes to embedded devices, this actually excites me to explore more about this world that is embedded AI, right? Because moving forward, so we are going to be surrounded with lots and lots of tiny embedded devices, starting from smart glasses, smart watches, and IoT devices for home automations. Everywhere we are going to see lots of tiny devices. Now the question is how to enable all these tiny devices with machine learning smarts. Then only we can do lots of things, right? So how to do it? Let's see. So that's all about the embedded systems. Now, let us uh, go one step further to understand what exactly the machine learning model size is. So here is the snapshot. Here you can see an exponentially increasing trend in terms of number of parameters over the years for most of the state-of-art machine learning models. Here you can see the number of parameters involved in OpenAI. It's one of the state-of-art models in AI. So what exactly the number of parameters I mean? So usually or typically machine learning models are characterized by model parameters. Anyway, I'm not going to get into the details, but I will give you some flavor about what exactly the parameters are. But as of now, you just take machine learning models are usually characterized by parameters. So if you take some of the state-of-art models, usually these models are you know, equipped with more number of model parameters. So you can see here, there are close to, see the number here. It's, I think it's 2 lakh million parameters involved in open a machine learning model, ChatGPT 3. Think about it. So it's not possible to flash a ChatGPT model inside a 128 KB sized embedded device. That's not possible, right? And now look at the compute power that needs from compute needs from 1949 to 2026. You can clearly here you can clearly see there is a extremely increasing demand for compute power because the number of floating point operations involved in most of the state of art machine learning models are extremely high. If you look at 2025, so from 2010 to 2025, we are in deep learning era. Anyway, I talked about what exactly deep learning is. So deep learning is a machine learning technique which uses artificial intelligence to learn complex patterns from a data. That's what deep learning is all about. There are lots of deep learning models available. For example, AlexNet and Gemini 1.0 Ultra. You see here, and the number of floating point operations involved is extremely high. Just I talked about the limitations of embedded systems. Embedded devices are limited in terms of software portability. It lacks floating point unit. But if you look at it's machine learning relies on floating point operations for precise calculations, right? So then how to merge or how to mix this machine learning and embedded systems together? That's the world I'm talking about. How to mix it. So we will see how a simple mathematics can help us to fit a heavy model into a small sized resource constrained tiny devices. I'll come to that. Just stay with me. Let us systematically understand uh, uh, the let us systematically understand what exactly the machine learning is. Now, let us go one step further into the machine learning. So, what exactly the traditional programming paradigm is and how it is different from machine learning programming paradigm. So, this is very, very important to understand. So then you can easily follow the numerical representations or the math task that I'm going to talk about in a while. So traditional programming paradigm, let us understand this. Very simple. So traditional programming basically, uh, you will strive to solve a problem by figuring out rules by writing some set of rules using C++, Java, Python, and all that. That's what traditional programming is. You need to solve a problem by figuring out the rules, right? So by figuring out the rules, and you need to write all those rules by using some programming languages like Python, Java, C++. Okay. So input to the traditional programmings are, yes, you need to figure out the rules. Rules you need to figure out, feed the data, and get the answers. So you have the data and you have the rules, and then you can get the answers. There is no big deal in traditional programming. Let us understand this through a simple example, activity monitoring. So consider this applications, that is activity monitoring is basically to recognize the human's activity like walking, running, biking, or golfing, for example. So, what you can do if you want to solve this problem by using a traditional programming, yes, you can write rules based on the speed. If someone, you know, uh, walks with a speed of less than 4, then you can label it as walking. If the speed is less than 4, yes, as I said, you can label it as walking. If the speed is greater than 4, then you can make the status as running. If the speed is greater than 4 and less than 12, then you can write a lot of conditions, right? So if the speed is again, uh, greater than 4, less than 12, then you can label it as biking. So likewise, you can write some set of rules, right? You need to figure out the rules. There is a problem. The problem is basically to recognize the human's activity. How to recognize the human's activity? You write a rule, and based on the speed, and you can write this by using any programming languages here, right? But there are situations where this solution fails. This traditional programming actually fails. For instance, you might run downhill fastest when run from steep. Then what happens is you run faster, right? In that case, this rule-based approach or the traditional programming will fail for sure. So that's what I mean. So you might run downhill faster because of gravity than you bike uphill. In that case, the system will fail. And say, for example, if you are golfing, if it is a completely a different human behavior, then in that case, also traditional programming will fail. So what if you look other way around by providing answers and data to the computers? Again, compare this. Just have a look. Traditional programming, we feed rules and data as input to get the answers. In machine learning, in simple terms, machine learning programming or machine learning paradigm is basically provide the answers and data and allow the computers or the digital machines to learn rules from the input pairs. That is what machine learning is all about. We are not going to figure out the rules and we are not going to express or write any code. Instead, what we are going to do is we are going to feed the answers and data to the computers and we are going to allow the computers to learn the rules. So computers will figure out the rules. So that's what machine learning is all about. For example, so this is a sensor data. So this is a sensor data and you see here there is a distinct pattern exists in all the sensor data. So 1001 and here four ones and 1011. So you just feed this information to the machine learning model and machine learning model will figure out the pattern. That's what I mean. Machine learning model learn patterns, unique patterns from the data. You feed the sensor data and the output label and allow the machine learning model to figure out the rules. So that's what machine learning paradigm is all about. How to achieve this? It's very simple. You make a guess and measure your accuracy and optimize your guess and repeat the process again and again till you reach a better accuracy or optimal accuracy for your uh, problem. So that's what. Anyway, we will understand this through a simple numerical math task. Just stay with me. So probably, I think this is what the headline difference between the traditional programming paradigm versus machine learning programming paradigm. Now, yeah, so this is something you need to understand what exactly the training phase and testing phase in the context of machine learning. So take a computer and feed answers and data as input to the computers and allow the computers to learn the rules, to figure out the rules. Once it is done, then take that rules, which means that is a model, you feed the data, which means now the rules act on the future data to make the inference. That's basically to get the answers. This is what the training phase and testing phase, training and testing generally we talk about in machine learning paradigms. So I hope this is clear to you, right? Now let us understand this paradigm through a simple numerical task, a math task. So let us take a pair of data, X and Y. So because the time is limited, that's why I'm slightly rushing a bit. Uh, but you can stop me but you can stop me and if you want me to explain uh, in slow, then that also I can do, right? Okay. So here you can see X and Y, some pair of data, minus 1 and the corresponding Y is minus 3 and 0, minus 1, 1, 1. Okay, so I have given some pair of X and Y values, numerical values. Now, there exists a relationship between, a linear relationship between X and Y. So that's a hint. That's a hint. So there exists a linear relationship between X and Y. So I can express Y as WX plus B. So this is basically a linear regression formulation or the linear relationship in simple terms. How to understand this? You pass X, then you will get the Y. But the question is, what about W and B, which is not provided in this data? Only X and Y is provided, but there exists a relation. Now, let us solve this by using machine learning. So, just I mentioned machine learning paradigm is basically to start with a guess, right? So that's how machine learning model will learn and optimize. You start with the guess. Let us start with the guess for W and B. If the guess is 3 for all W's and if the guess for B is -1, so now you substitute and see. So what happens? X is -1, W is 3 means -3, and B is -1. So what you will get? So you will get -4 as a result and -1 as a result for the second pair of values. Likewise, you can compute all the Y's. But you just compare this Y and the predicted Y. So there is a difference, right? So -3 is the actual output, but what we have predicted is -4 because our choice of W and B are 3 and -1. So yeah, we start with a guess, but that is not correct. So what is a loss? Try to measure the accuracy of our predictions or the choice of parameters W and B. So that easily you can, identify by computing the loss. So what is a loss? You just subtract the and the predict. So -1 is the loss and 0. These are all the loss. It's a simple uh, difference. Then try to square the loss. Why to square the loss? Because here it is -1 and here it is 1. So the whole idea of machine learning is to minimize the loss. So you should not think that -1 is the minimum value. That's the reason why you always square the loss so that it becomes absolute. Now the whole idea is for my first guess, W and B. So this is what the loss. Now I need to minimize the loss with respect to the W and B. So this part is what primarily we discuss in high level machine learning course or in undergraduate level or in typical machine learning course. How to minimize this loss with respect to the W and B. Because I need to update this W's and B, right? So how to do it? So there is a concept called as gradient descent. So it's basically you minimize the loss with respect to the model parameters, that is W's and P's. That will give you the gradient. Gradient basically tell us the direction towards the minimum. So just make a note of it, and if you need any details, you can explore more about it. What exactly stochastic gradient is all about. Now, when you try to minimize this loss, and if you were updated weight, yeah, you need to minimize the loss and you need to update your weight with some calculations. And if the updated weight is 2 for W and B is -1, then now if you look at the predicted values in the second iterations, if you look at the predicted values, now it is same, right? The Y predict and the original Y is Y, both are same. So now if you calculate the loss or the accuracy of your predictions, that is 0. The loss is 0 means it's 100% accurate. So the hidden value for W and B are computed through this paradigm, and the values are basically 2 and -1. So this is what machine learning is all about. This is what internally happens inside machine learning. So you start with machine learning starts with a guess, and it will try to compute the accuracies through loss, and it will try to minimize the loss by using some stochastic gradient method, and it will try to update the model parameters. The model parameters, I mean the W's and P's, and this process continues over multiple iterations till the loss becomes 0, or otherwise the accuracy reaches close to 100 percentage. So this is what machine learning is all about, and I hope this gives you a clear understanding about the internal mechanism of machine learning. So for this problem, the solution is W is equal to 2 and B is equal to -1. Okay. So I didn't discuss much about how to update this weights. So as I mentioned, this will take us to stochastic gradient process. It's a statistical process. So anyway, just make a note of it and you can explore more about it. So this is what the loss function, and this is all about that minimizing the loss with respect to the model parameters that will give you the gradient, and gradient tell us the direction for minimum because you need to minimize the loss, right? Okay. So this is all about machine learning. Now, coming back to the question of how to pack a machine learning model inside a tiny device. That's what we are interested in, right, in this presentation. Because most of the machine learning, you know, computations usually happens in floating point. So the natural choice is cloud. Natural choice is cloud because GPUs or TPUs, can handle floating point math better. So that's why the natural choice is cloud. So now, how to move from floating point to integer representations? So let me give you a simple example to understand this. For example, all the computations inside machine learning, everything happens in float. Float in the sense some decimal values. But we don't have the privilege to store all the decimal values inside a tiny embedded devices. That's a problem, right? Then how to solve this problem? So by using a simple quantization technique, that's basically to represent a floating point number into a integer number, then you can solve this problem. How, for example, if the value is 2.7, let us take a float number 2.7. And now if this 2.7 is within the range of minus 3 to 6, so here is the simple mathematical, closed form solution to convert a float value to an integer values. What's this mathematics says? So it's very simple. W minus minimum divided by max minus minimum into 255, that is a total range of int, and then you round it off. So take the number, floating point number 2.7, and the minimum is minus 3, and the maximum is 6, and substitute here, you will get 0.6333. It's a decimal value. Again, you will end up with a float value. Now, what you do is try to round it off. Round it off, but before that, you need to multiply with 255. When you round, you will end up with 162. So the floating point value, what we have is 2.7. Now you apply a quantization techniques basically to round it off to a whole number, that is an integer. 2.7 is equated to 162. So 162 is an integer in 8 representations. You can comfortably store this value inside any tiny microcontrollers, right? That's the power. But in order to make the inference, you need the float value, right? So how to dequantize it back? So dequantize it back in the sense 162, again, you just carefully look at this expression. You can get this W by using this Q. How to get it? So if you just use this solutions, you can get back the original float values. 162 divided by 255, 9 minus 3, which will give you 5.716, minus 3 will give you 2.716. Okay, let me summarize this, what exactly this process is. Floating point values are usually, float around inside the machine learning computations. But the problem is you cannot handle float values inside any embedded device. Embedded in the sense tiny ultra low power device, because it lacks floating point arithmetic operations, floating point hardware. So there is a technique to move a float value to integer values. So 2.7, for example, is a float value, then just equated to 162, that is an int 8 representations. At the time of inference, what you can do is you can introduce something called as fixed point arithmetic. It's a simple, mathematical number representation. The fixed point arithmetic is basically 162 has to be scaled by some values to get the float value back. So this is what the floating point to integer representation, which will help us to fit a heavy machine learning model into a small, tiny device. So what are the compelling advantages of 8-bit integers? So the one advantage is usually if you want to represent a number in float 32, then it takes 32 bits. And if you look at int 8 representation, it takes only 8 bits. So memory wise, if you look at, it's going to be very, very less, right? You can store a lot of informations compared to the float 32 representations. So, and if you are performing any addition, float-based addition or force-based multiplications, this is what I mean the computations. Usually this takes approximately 3 to 6 CPU clock cycles. Whereas if you involve or if you have all the values in int 8, then it takes 1 clock cycles, roughly approximately 1 clock cycles, which means all this in calculations, you know, uh, runs faster compared to the float based arithmetic operations. So, and the model size, if you look at, usually the model size will be large when it comes to float 32. And if it is represented in terms of int 8 representation, there will be a drastic reduction in model size, 4x reduction with respect to the float 32. And coming to the energy consumptions, because the number of cycles involved is more when we perform any arithmetic operations with float. So that's why the energy consumption, the energy per operation is higher in float 32, whereas in the case of int 8, it is much lower. So that's the critical message I would like to convey here. The When you try to move from decimal to integer whole numbers by using a simple quantization techniques, you can actually pack the heavy machine learning models into a small, tiny devices. So here is a snapshot, and here is an example for you to understand. This is actually a part of something called as post-training quantization. Is one of the highly celebrated and widely studied machine learning technique in the context of embedded AI. But just to give an example, same regression problem, let us look at. So y is equal to x into WFP32. So 0.5 is x, and anyway, I will share the slide, or otherwise, once it is uploaded in YouTube, you can carefully go through this calculations. So this is what the result you will get. But instead of using the floating point value, what if you use the context values? If you use the whole number, yes, you can use the whole numbers. Use the same strategy and move the floating point value to int 8, then you will end up with 66. But at the time of inference, you need the float value. So for that case, you just go for the fixed point arithmetic. That is not floating point arithmetic. Please understand that's basically a scaling process. So what's that scaling process I mean? This is what this 66 into 1 by 255 is the scaling. This is the fixed point arithmetic. You perform it, you will get the values closer to the original floating point value. So with the help of this idea, you can pack a heavy machine learning computations into a small devices, computing devices. So, so this is what I mean. The advantage of using integer representation, it's just a number representation over floating point representations to, you know, run AI models into small, tiny devices. Now, I would like to, so yeah, just give me 5 minutes. Let me give you some idea about an applications which, helps you to understand the embedded AI better. So as I said in the beginning of my session, keyword spotting, that is, hey Siri, okay Google, and hey Alexa, when you say all these words, the machine instantly wakes up and start responding to it, right? So this is actually the anatomy of hey Siri inside an Apple iPhone. So the moment you say hey Siri, it goes to the core audio, and then it goes to a small embedded device where the keyword spotting application is actually embedded. Keyword spotting application, in the sense, it's a machine learning model. That machine learning model, it's a tiny machine learning model that helps you to trigger the missions. Then after that, it can go to a large neural network space where you can do all that speaker identifications and the voice recognitions and all that stuff. You can do it. And if you want to perform a heavy task like, yeah, can you please play my favorite song? You cannot do it inside a small device, because play my favorite song is a heavy task. So then in that case, you cannot expect that applications inside a small device. It's a heavy application that requires lots of computations and lots of data processings. That's why that applications goes to the cloud servers where it process. So depending on the applications. So let me clarify this again. If you say a word, hey Siri, it's just a simple word you are saying to the smartphones, and the machine instantly wakes up and respond to it. So that you can do it in the local system itself, in the sense in the inside the smartphone itself. But if you want to perform some applications like play my favorite song, that is a heavy task. It requires lots of processings. Then in that case, you need to push the query to the cloud servers, and there you need to run some heavy deep learning models to perform that task. This is the headline difference between the cloud-based machine learning and the edge-based, or otherwise the tiny machine learning is all about. So yeah, I have few slides to wrap this presentations. Just give me 2 minutes. Let me finish this so that it will be complete. So coming to the system architecture of keyword spotting, as I said, your embedded system is going to continuously listen on the microcontrollers. It's going to continuously listen to the words, and then it is going to, yeah, sorry. Yeah, so it goes to the microcontroller, and microcontroller runs some tiny machine learning models to perform the keyword spotting applications. As I said, if you want to perform a heavy task, then it goes to the cloud and to perform that heavy applications. So here is the simple demonstrations. So you can write a machine learning code using TensorFlow. TensorFlow is a software framework where you can write the machine learning code. So you can run a machine learning code in TensorFlow. It's Google's machine learning platform. Then you convert your machine learning code or machine learning trained model into a light model by using TensorFlow Lite, and then you flash it inside the Arduino board or otherwise Raspberry Pi or ESP32. So you can take any embedded boards and you can flash it inside the hardware. So here I have a small, microcontroller. This is actually a development board, but if you look at the core, this is actually Express if32. It's a very small microcontroller unit. And say, for example, if I want to enable machine learning here, right? So what I do is I will write a machine learning code in TensorFlow, for example, and then you try to convert that code into a TensorFlow Lite, and then try to flash it inside this microcontroller unit. This is a pipeline. This is a fundamental pipeline. But one thing you need to understand, or one thing you need to investigate is whatever the machine learning code you write in TensorFlow, you always look at the size of the machine learning code. Most of the state of art heavy machine learning models, if you look at the size, will be in terms of MBs. But this microcontrollers, for example, it has the maximum capacity of just 256 KB. Then in that case, you cannot flash that code inside this microcontrollers. So you have to make the model as light as possible. There are lots of lightweight architectures available, or otherwise you need to strive to make the model light without compromising on the accuracy and latency. So here you can see, so here is a video which demonstrates the keyword. Okay, when you don't say anything, then this yellow blink, and when you say yes, then this green light will blink, and the moment you say no, this red light will blink. So this is the successful implementation of uh, you know uh, which is more or less close to what is available in Hey Siri, Alexa, and OK Google. So yes, you can actually build some keyword spotting applications by using an embedded board. And if you have an embedded device and TensorFlow, you can experiment on this. So one thing you always don't think that the entire KBs of memory is for machine learning models. No. So there are other tasks you need to run inside hardware. So you cannot use the complete space of RAM for flashing the model. You need to give some room to perform other tasks like audio buffer and application to run the application codes. So this is something very very important. When you write machine learning code, it has to be optimized in terms of memory, inference speed, and computational power. So that's very very important. And yeah, with this note, I would like to uh, conclude my presentations. So machine learning code is a very small part. It's a very small part in a machine learning systems. If you just look at from a system point of view, machine learning code is just a small portion. Right? Machine learning code in the sense to develop a machine learning model I'm referring. So machine learning systems is more about engineering and the operations beyond machine learning code. So that is what you need to focus on. So Writing a machine learning code is not a big deal. There are other aspects that you have to focus on. Engineering, you have to focus on beyond machine learning code. So to build a complete machine learning systems. So with this message, I would like to conclude my presentations. If you have any questions, I can uh, answer a few of them. Yeah.
Thank you, sir. So participants, if you have any questions, so you can post in the chat box or in the Q&A section. So sir will be happy to answer that. Sir, at registration, there are two questions from students. So
Yes, yes,
one
please.
is the student has seen the embedded systems code at the School of Computing and Science BTech program. Right? So
Yeah.
his question is, will this be a practical program or embedded systems? That's his question.
Yeah. Okay. See, we offer embedded system course as a part of BTech Computer Science and Data Science program. So embedded system course, what we have at Sai University is completely on hands-on perspectives. In the sense that this course usually handled by Professor Saraswati. Um, so you can review her profile in Sai University website. So usually this course stitched with a robotic competition, a flagship robotic competitions called Yantra. So this is not a typical classroom course. This course usually happens in the laboratory where professor will give hands-on training on all the embedded system concepts through robotics. That's how the course was tailored, and that's how it was taught so far in School of Computing and Data Science at Sai University. It's completely a hands-on course, and and more inclined towards robotics. So robotics is a kind of embedded systems where students will pick some of the boards like Arduino, Raspberry Pi, and there they will experience some of the digital logic principles and computing principles. That's how usually that course happens at Sai University. It's a completely a hands-on course. Yeah. But I would like to add a small point. In addition to embedded system course, we offer courses like machine learning, deep learning, and tiny machine learning is the course which generally offers. So these are all the courses where we will, bridge the embedded system concepts as well as the deep learning and machine learning concepts together. So, tiny machine learning is a course where students will get an experience or exposure to, mix embedded system hardware and machine learning software together uh, to to experiment some of the potential applications like keyword spotting, anomaly detections, and object detection. These are all the typical applications we generally teach in tiny machine learning course. So just to give an glimpse, so we have embedded system course, software engineering, and machine learning, deep learning, AI, and some of the application courses like tiny machine learning or machine learning system design, and MLOps is the course which I'm going to offer next semester. That is machine learning operations. So just to give an idea, so machine learning operation is MLOps. It's similar to DevOps. It's a potential area that people are talking about now. How to make machine learning model into production line. So that's what machine learning operation is all about, right? It's not about just writing a code, writing a code. So that you will do it in the deep learning and machine learning course. When it comes to tiny machine learning course, where you will mix both embedded systems and machine learning and deep learning. When it comes to the advanced courses like machine learning operations or machine learning systems in production design, these are all the unique courses we offer at Sai University. That course will help you to understand how to make the machine learning model into the business line, in the sense in the production line. So you will get, you know, all the complete stack of machine learning will be covered in the CDS curriculum, that is School of Computing and Data Science curriculum. Yeah, hope this is clear too.
So much. And there is one question from Santosh here. I think he's not joined this webinar. But
Yeah.
so this question is, I'm interested to become a programmer, but I'm confused to choose between BTech Computer Science or BTech AI. So which should I choose?
Uh, okay. See, BTech Computer Science is a foundation course, right? So I would like to give this information to most of my students. Like, so the paradigm will change. Currently, we are talking about AI. Soon, the paradigm will change. People will suddenly talk about quantum. So, so as you see, the paradigms will change over the years. But once you have the foundations, so once you have a strong foundations on computing principles, that is basically the computer science, then you no need to worry about it. Even the paradigm changes. So I recommend. So if you are interested into strengthen your foundations, then in that case you can focus on BTech Computer Science. Or if you want to straight away jump into the current job market, or otherwise the current market, that is AI, then you can straight away jump into the BTech Artificial Intelligence. Both the courses, if you look at, even in artificial intelligence, BTech AI, though it is offered by School of Artificial Intelligence, a different school at Sai University. So they also cover the basic programming and some computer science principles, but they don't go deep into the computer science principles like DBMS or operating systems. So whereas in typical computer science course, you will get all that foundational informations. So it depends. If you want to straight away jump into the AI domain and you want to experience it, then straight away go for BTech Artificial Intelligence. It's an advanced offering, I would say. And BTech Computer Science, yeah, it's a foundational program. It's a typical program, I would say. But in that program also, we cover artificial intelligence, machine learning, and deep learning. So it depends. It depends on your interest. Say, for example, if you are interested in Internet of Things, for example, then in that case, you need to understand some of the computer science principles like operating systems and DBMS. So that will not be covered in artificial intelligence. So it depends. So I think it's better to, you know, uh, pursue BTech in computer science with AI specializations, because we have a specialization here at School of Computing and Data Science. So that will give you a good balance between computer science and AI if you are interested in. Or otherwise, as I said, so you can straight away jump into the AI and you can learn about large language models and advanced AI principles like generative AI and other aspects of AI. So there are two different paths depending on your interest and what exactly you want to do after 4 years. So you can pick any one of that.
Great, sir. Thank you. So I think final question is from our admissions team. So I think there are a few applicants over here, so who have yet to complete the application. So if from your perspective, if you can say just three reasons why School of Computing and Data Science at Sai University is exclusively from your point.
Okay, right. See, there are lots of universities in India offers liberal education in tech as well as in arts and science. So one unique thing about Sai University, from my experience, I'm not here to sell Sai University. So one unique thing about Sai University is that it's one of the very few universities in India offers liberal education in tech domain, especially in computer science. So that's actually a very unique program. In what way? So let me explain a bit about it. So you can pursue computer science as a major, and you can also pursue minor in biological science. What's this kind of a mix? Typically, you don't find these kind of mixtures in other universities. So, but the current NEP or otherwise the Western educational systems, if you look at the holistic learning, or otherwise, the multidisciplinary, interdisciplinary knowledge is extremely important, because the current job market actually demands people, the candidates, not only with technical skills, but also they want people uh, to have skills beyond their technical domains, because there are lots of job opportunities like policy making. There are n number of opportunities, non-tech opportunities also available. So they need a multifaceted, or a multidisciplinary person. So that's how the job market is. So that's why having a knowledge on different domains, so that definitely will help as we move forward. So where you will get this kind of educational model. So Sai University, I would say, is, as again I repeat, one of the very few universities in India offer liberal education in tech domain. So so that's what you can pursue computer science with AI specialization. You can pursue computer science with data science specialization, and you can pursue computer science with biological science, psychology, economics. So you can mix your tech with other arts and science courses, or even with some tech courses. That's the beauty of this educational model. And coming to the uniqueness about School of Computing and Data Science, so we generally offer all, foundational courses, foundational in the sense tech foundational courses covering operating systems, DBMS, programming, C, C++ programming, OOPS programming, Python programming, all that foundational courses will be covered for sure. So in that way, we are, you know, we are in the same line with what other typical universities offers. On top of it, we have different academic pathways for computer science, data science, and computing and data science, and even computer science with AI specializations. There are different multiple pathways we have. So it's not necessary that you need to learn all that 64 papers throughout 4 years of time. So we have dedicated pathways, and so you can define your own academic pathway. That's the beauty of liberal education. And even in School of Computing and Data Science, also we give complete flexibility and opportunities to the students to design their own academic pathway with the help of faculty mentors. Yeah, definitely you will get mentorship from faculties, but you can define your own academic pathways. What exactly you need to learn, and which course you want to pick, and what time you want to pick. Everything you can customize. Yeah, obviously certain courses are mandatory. Yes, then certain courses follow some prerequisites. Yes, you have to follow it. But on top of it, it's not about all the courses you need to learn or you need to earn the credits by sitting and listening to lectures in class. There are non-classroom credits which comes with significant credit points. You don't need to, sit and learn in class. So which means you can, earn some of the credits using non-classroom credits. That's basically reading courses. You can sit along with the faculties and you can learn some advanced concepts. So there are a lot of verticals we have at School of Computing and Data Science that gives you a very nice learning experience, flexibility and opportunities. So as long as you get the opportunity and flexibility for learning, you can do lots of things. That's what the uniqueness about School of Computing and Data Science, I would say. And moreover, coming to the courses, all the courses will be, handled or treated in a very, very rigorous fashion, I would say. So because there is no typical examination procedures applicable to all courses, because here all the courses are under the discretion of faculties. Faculties will design the curriculum, faculties will design the course descriptions, and they will offer the courses their own style, because they know better what sort of assessments they need to uh, carry out. And moreover, the continuous evaluation process what we have is something unique, in the sense we assess the students' performance not at the end of semesters through end semester examinations. We assess the performance of students throughout the course time. So that's what we mean continuous evaluations. And moreover, there is no typical structure like two exams, three exams kind of schemes. So each and every faculties have their own grading schemes and and the assessment plans. So in that way, all the courses are going to be unique, and that will give you a very, very nice experience, I would say. And so you can enjoy the process of learning throughout 4 years, and you will also get the practical exposures to some of the latest courses like AI, machine learning, because all the courses we offer here, most of the advanced courses we offer here, for example, deep learning, machine learning, Internet of Things, and computer visions, natural language processings, all these courses are discussed in a practical manner. So it has course projects, and this all these courses comes with very interesting assignments, which will make you to think and explore more. So overall, the flexibility and opportunity at Sai University and within School of Computing and Data Science uh, will make your learning process enjoyable, I would say.
Thank you so much, sir, for such a detailed answer. And
Yeah.
with that, we're in the final verge of completion. So, thank you, participants, for attending the session. And you can find the recordings in a couple of days in the YouTube channel, so you can share it with your friends. And if you're already applicant, probably get in touch with our counselors. They will guide you with our admission process. Or even in case you want one-on-one session with sir for any if you have any queries, you can connect with our faculty team along with sir as well, and our counselors will help you out with that. Yeah. With that, thank you so much, sir, on spending your time on a Sunday morning, and thank you, participants, for joining. Thank you.
Thank you. Thank you all. Thank you. Thanks for joining.
Yeah.
Thank you all. Thank you. If you have any questions, please feel free to connect me through email. So, thank you all. Thank you.